I'm not sure if Pablo needs an intro, but I'll do one. So Pablo Samuel was born and raised in Quito, Ecuador. Hopefully I pronounced that right. And moved to Montreal after high school to study at McGill. He obtained his PhD from McGill, focusing on RL, under the supervision of Doina Precup and Prakesh Panangadan. He's been working at Google for over 12 years and is currently a staff research scientist at Google DeepMind in Montreal. And he's focusing on fundamental RL research. He's also an adjunct professor at the University of Montreal, a core industry member at Mila, and a regular advocate for increasing the Latinx representation in the research community. Aside from his interest in research and coding and AI and math, Pablo Samuel is also an active musician. And I think now also he likes to run, so I'll add that. So a man with many talents, and we're really excited to have you join us here today, Pablo. So yeah, take it away.
Thank you. Thanks for that intro. Yeah, very happy to be here. Thanks for the invitation. And I'm here presenting work done jointly with all these fine people shown on this slide. This is a paper we put out on arXiv a few weeks ago or a month ago, where we were exploring the use of mixtures of experts in online deep RL. So I won't go through all the names, but you can see them all there. I just wanted to highlight the first three authors that are in that green box are co-first authors. So this is Johan, Ghada, and Timon, and I think Timon is on the call. I think Johan as well. Okay, so let's go right into it. So a lot of this, the motivation for exploring this is something that we've been noticing in our work over the past few years. I mean, you'd be likely very stuck in your research hole if you didn't know about scaling laws and you haven't heard the discussions on scaling laws, especially around large language models that people have been really excited about. And I mean, this excitement is what has drawn people to train ever larger models with ever more capabilities. And so this is a paper, I mean, by today's standard, fairly old, but it's only from 2020, where this is from a bunch of OpenAI folks, where they were showing that as you increase the model size and dataset size, your loss tends to go down. And so this is not just loss, you also see better capabilities with these models. And so people have really been pushing the limit of these scaling laws to be able to train better and better models by quote unquote simply making things bigger. But it's really hard to do in RL. So especially in online RL, which is where I focus most of my efforts. So this is just a simple example where we have a standard value-based network here. This is what we typically use for most algorithms that are based on DQN. And so you have an encoder. This consists of a set of convolutional layers. And then you have these two fully connected layers. So in this plot here, what we're doing is we're scaling up this penultimate layer. And we're scaling up the width, and you can see this totally tanks the performance. So we're really unable to scale networks in a way that works well for us. And this is not just something in that specific setting. I mean, this is something, as I mentioned, we've seen in a lot of our own work, but others have also noticed this difficulty. This is from a paper we presented at ICML last year, BBF, where you can see that as you increase the number of parameters, most algorithms either plateau or start, collapsing after an increased after a certain amount of parameters. Our BBF agent, as we're arguing here, obviously doesn't do that. It is able to scale up well, but it required a lot of quote unquote tricks to get this working. These are all the components we had to include in BBF to really get this working. So we had to use things like self-supervised losses that came with SPR, with resets, with network resets, and we had to use harder resets. A big part of it was this larger network, but this larger network, we couldn't just do it on its own, so it had to be coupled with some of these other factors that we included in our agent. And this is an ablation plot, which I quite like, which shows the impact of removing each of these things. And you can see that the resets is really what causes things to collapse. And I think this is something also consistent with a lot of our work. The whole premise of network resets, which you may or may not be familiar with, this started gaining popularity with this paper from, I think, 2 years ago by Max as well, who's the first author of this paper, called The Primacy Bias. Max, Evgeny, and Pierluca, the co-first authors of that paper. And they demonstrated that networks in reinforcement learning have a tendency to overfit to early data. And this is not just with early data. So we have seen evidence of neural networks for RL overfitting to the data in general. And so this makes it difficult for it to learn new tasks. And as we know in RL, the data that we're receiving is totally non-stationary because we're collecting new data. And the way we're collecting new data is with our policy. And our policy is changing every time, right? That's the whole point of RL. We want to improve our policy. So the input data is totally non-stationary. The target is also non-stationary because for these value-based agents, we use this thing called bootstrapping, which is basically reusing prior estimates to construct new targets. So we have this very non-stationary setup for learning, which makes it it's part of the reason why it makes it difficult to do things like scaling and why a lot of the insights that we see in supervised learning don't carry over to RL. So one thing we have been observing as a community is that a big component of these new large language models and foundation models, as they're sometimes called, are these mixture of experts. So these mixture of experts bring a number of advantages with them. Obviously, they allow you to scale, they allow you to get better performance, but they also allow speed ups in terms of inference, especially when you're doing sparsely gated mixture of experts. And I'll get into what that means in a little bit. Because you can do things like distribute these experts across different devices. And when you're doing inference, you don't have to do the inference on all these devices, just on a few if you're using sparse experts. And so this notion of a mixture of experts was something that I was drawn to in particular because I've done some work in sparsity, both in reinforcement learning, but also in supervised learning settings. And with my collaborators, we were always kind of interested in these mixture of experts. One of them is an expert, Trevor Gale, who's the first author of this Megablocks paper. He was also always, telling us about the wonders of mixture of experts. So it's something we always had in the back of our mind. And in the context of all this difficulty with scaling and the non-stationarity of RL, I was curious if something like this could help. And so this is sort of where the project started off. Okay, so before getting into some of the details, let's describe what I mean by mixture of experts. So the way we use mixture of experts now, I mean, it can mean many things. So you can think of ensembling, which is a technique from decades ago as a form of mixture of experts. But when we talk about mixture of experts today, typically what we're referring to is this idea that was, I think, first introduced in 2017 by Noam Shazier and co-authors. And the idea, this was introduced before transformers. So the graphic here is using RNNs or LSTMs, some recurrent neural network. And the idea is that you have, when you're doing this forward pass through your network to get your new hidden state, you add these MoE layers. And what these MoE layers do is rather than having, fully activating all of the parameters inside your module here, you're going to have a set of N experts, and you're only going to pass the data through a couple of them, like one or two or just a few. And how are you going to select which ones you're going to do the inference on? Using this gating network. And this gating network is affected by the input, and it also has learned parameters. So the network is learning how to do this routing. So in this paper, it's called the gating network. Nowadays, it's often referred to as the router. And so what happens here is you have these N experts. You feed in your data through here, and now not all of these experts are going to be providing output, only a few of them. And those few then get combined, and then that becomes the output of your module. And so they showed that this really helps performance, but more importantly, it allows people to scale these networks to a level that wasn't possible at that point. This is from the Megablocks paper. It's another way of looking at these mixture of experts where this is using more modern terminology where you have tokens. So now this is within the context of transformers, which is where people are using these right now, mostly. So you have a series of tokens that come in as your input, and these get sent to the router. And each of these tokens then is going to be routed by the router into different experts. So you have your experts here, and each expert has a specific capacity in the traditional way of thinking about mix of experts. So in this case, these experts have a capacity of 2. That means that each expert can take on 2 tokens at most. Okay, so some experts might be very popular, and so there might be some lots of tokens that want to go to those experts, but the experts can only take 2. So the top 2 will get sent to the expert, this first expert here, and then expert 1 will take some other 2 tokens, etc. There may be fewer experts than there are tokens, so some tokens will get dropped. And this is something that Trevor was trying to address in this paper, trying to deal with this issue of dropped tokens. So in any case, I won't go into too many details there, but the idea is that each of these experts processes the tokens, comes out with an output, and then this gets combined. So you can see that if you were to put a black box around this, this kind of just looks like a fully dense network, right? You feed in your tokens, and then the output of that are the logits or whatever from that module. But the experts internally allow you to have this modularity and this sparsity that you can then distribute things, distribute computation, or shard your data, etc. And it allows you to scale and gives you better performance. Was there a question or?
Maybe I had one just quickly. Like I understand in NLP how you have like drop tokens because the sentences are not always the same input length, but in RL couldn't you have like you always have the same number of tokens, right, per input? So would you also have this issue of dropped tokens?
So first, typically in NLP, even if you have different sentence lengths, the input it's usually the same, and they'll just pad things at the end. And this is just for architectural reasons. For RL, I'll get into the tokenization in a little bit.
Okay.
What happens? Sure. Okay, so feel free to interrupt me, by the way, at any point if you have questions. So what I mentioned here, this is what's called hard gating, where you essentially, the router assigns 1 expert per token, and then the token may or may not be dropped. But this paper that was introduced last year by some colleagues introduces the idea of soft MoEs. So rather than assigning, like I mentioned, each token to an expert or just getting dropped, soft MoE, what it does is it assigns, you can think of part of a token, right? So the token can get assigned to multiple experts, but it's weighed differently. So each expert can now take in a certain number of slots, and each of these slots are parts of tokens. So you essentially end up activating all of the experts. You don't have this type of sparse gating that we have with the traditional MoEs. You end up activating all of the experts, but each expert isn't committing to full tokens or to single tokens. They end up with a distribution of this combination of different tokens. And so the authors demonstrated that this tends to give pretty good performance. You don't have necessarily the inference gains, but in training time there doesn't seem to be a whole lot of slowdown. Okay, so soft MoEs is something that we're going to be exploring quite a lot.
Pablo, sorry to interrupt. Just a quick question. We have a question in the chat. Someone asks, are the hidden layers now the experts in this case? Or...
That's a good question. I should have included one of the standard transformer diagrams here. So if I come back here, if you can picture the transformer diagram that we've seen multiple times, it consists of the multi-attention heads, and then you have these feed-forward layers. This is both in the encoder and on the decoder side. MoEs are typically replacing those feed-forward layers in the transformer architecture. But in general, they tend to be used to replace, yes, the hidden layers, the hidden dense layers. So rather than having like a single layer here, which is what you would traditionally have, now you have this MoE module where you have multiple experts.
Okay, cool. Makes sense.
Okay, thanks. Thanks for the question. Okay, so soft MoEs has this idea of combining weights of tokens, and the math I won't go into too much. You can check it out in the paper, but it's essentially what it's learning is what they call a dispatcher. So it's this matrix D here, and a combiner, which is this matrix C here. Again, I don't want to get bogged down in the math. You can read that later in the paper if you want. What's important here is that what's being learned is this phi matrix, okay? And this phi matrix you can see is used both for the dispatcher and for the combiner. Sorry, was there a question? Okay,
no, I think it was someone's mic.
Okay.
Yeah, sorry for that.
Okay, so the phi matrix is what's being learned here. I always like pictures more, so this is a picture that they include in the paper. And the idea here is this is our phi matrix. These are the weighting logics that are being learned. And so you have these tokens coming in. Each expert now, rather than having a capacity for a certain number of tokens, they have certain slots. And each of these slots can be filled in by a linear combination of the different tokens. And so how are we going to combine these linear tokens, these tokens for each slot? That's what the dispatch weights are telling us, this matrix D. And then the same weights are going to be used for combining. So the each expert processes the slots and produces the output for each slot. And the output of each of these expert slots are then combined in a linearly way. And this is the combiner matrix that we have here. That's, again, coming from our learn matrix phi. And then you have the output linear combination is essentially has the same shape as the input. And this is something that's pretty standard in the use of MoEs. That makes it kind of transparent for the outside. When I said, if you put a black box, it just looks like a fully dense network. And that's because the input shape typically matches the output shape, right? And then there's all the magic kind of happens inside. So these are soft MoEs. They seem to work quite well in supervised learning. There's been quite a few follow-up papers from this. And now that we have that background, we can go into the RL part of the talk. So why study mixtures of experts for RL? I already hinted at this a little bit, but there's other reasons that I felt were quite interesting to do this. So I'm particularly interested. Yep.
Sorry to interrupt you. I just had a question on the soft MoE bit. Can you still do like a distributed training when you have a soft MoE, or is it something you can only have with a top?
Yeah, you can still do it.
MoE?
You can assign experts to different devices, but you might not have that distributed, sparse activation.
Yeah, because you have to call all of the experts anyway. Okay.
Yep. So one, I'm particularly interested in understanding how these neural networks work that seem to give us so many advantages. Most of the mixture of experts work that's been done so far has been on NLP and vision. And as I mentioned, whatever insights we get from that community don't always transfer to RL. Nowadays, most of the work is also happening with transformers. I mean, it's kind of a standard formula. If you use MoEs, there's a very specific place where you put them in. This is potentially experimental overfitting in the sense that we're not necessarily exploring different ideas. With RL, we have a green field of design choices to choose from. And so I'm going to get into some of that a little bit later. But I feel like exploring these MoEs in sort of this new setting, not only does it have the potential for helping us RL researchers develop better networks and thereby better agents, but it might also give us some insights into the learning dynamics of MoEs that could maybe be useful for the supervised learning community. There's some connections to meta learning, the router that we talk about. You can, if you squint, you can think of it as an agent. And in fact, there's been some old work that was trying to do something like this. This is not Joshua Benjo, that's his son, Emmanuel Benjo. And it was interesting work. I don't think it worked very well, but perhaps it's something that can be revisited. And there's new architectural or algorithmic ideas for MoEs, like these dropless MoEs that Trevor was introducing, soft MoEs, etc. And as maybe RL can become a new framework to evaluate some of these new ideas. and provide extra incentive for hardware low-level support. And of course, our LHF. This is something that is very much in the zeitgeist right now. Because we're doing RLHF on these pre-trained transformer architectures, if we can understand the RL learning dynamics a bit more with these architectures, then that could presumably help a bit more. Okay, so how did we do it? How did we use MOEs for RL, at least in this work? The first decision we had to make is where to place these MOEs. As I mentioned, the standard formula with transformers is to replace the feed-forward layers. And in fact, I don't know if there's been any work really in using MOEs in convolutional layers. So what we decided to do is, we have our standard value-based architecture here. We decided to take the penultimate layer, which is a dense layer, and replace that with a mixture of experts, as we have here. So after our ReLU, instead of going straight into our network, we're now going to have our gate, which is either a router or a dispatcher for using Soft MoEs, which then sends things to the experts. And then we're going to have our combiner, which might be for Soft MoEs, or it might just be a simpler waiter for the regular MoEs. And then we have our ReLU or nonlinearity at the end. And finally, we have our linear layer that gives us our Q values. Okay, so as you can see, if we look at these, I explicitly drew these in the same size as what we had here, because the experts are taking the same dimensionality as the penultimate layer that we used to have. So what we're effectively doing is adding more parameters to our network. And so in order to compare the effect of doing that with simply just expanding that layer, we can do exactly that, right? We can just take this penultimate layer and just widen it by the same number of experts. So here we're adding 4 experts, so we can just widen this by 4x. And we're going to be using this as a baseline to compare the performance of our methods. So what flavor of MOE to use? We decided to explore in this paper 2. The first is the standard MOE that does hard gating. And there's different ways of doing this hard gating. It's called top K gating, where you essentially select the top K each token selects the top K experts. There's been work showing that top 1 is usually enough. It's a lot simpler, both infrastructure-wise as well as training-wise. So we decided to stick with that, but it is something that we'd like to explore a bit more. There's been some recent work where they're starting to push that K value up to 2, and I think even up to 4 or 5. But again, this is in supervised learning settings. For our situation, we decided to use top K or top 1 hard routing, and we're also exploring these soft MOEs that I already introduced. Okay, and now to Samuel's question, what is a token? In NLP, we kind of get these tokens for free. They're the words to get tokenized, and that's sort of the currency that transformers are operating on when learning. In Vision, we also have a pretty clearly defined notion of tokens. If you're using these patches or what's it called? VIT. The Vision transformer is using these patches that become the tokens. And so that's why they can use transformers, because they have a clear notion of what a token is. In RL, we don't have that. And this is both a double-edged sword, because it gives us this green field of things to explore, but it also gives us a green field of things to explore. So there's a lot of ideas you can try. And so we did try a few. Because we're using the output of the encoder produces a tensor, a 3-dimensional tensor, where we have a width and a height and a depth. And so you can think of different ways of tokenizing this. You can think of having d-dimensional tokens, and because of the shape of this, we're going to have h times w of these tokens. Or you can just take the transpose of this and say we're going to have d tokens, each of which will have dimensionality h times w, and we call this per feat. Stands for per feature. And another simple one is you can just do per sample tokenization, where you consider this whole thing a token. And so here you in the hard gating case, you're really just activating one expert per forward pass. Whereas when you have multiple tokens, you're likely activating all of the or many experts. In the soft MoE case, it's a little stranger what per sample means, but we can get into that later. There's obviously more ideas you can try, and we have tried a couple more, but these are the three that we focused on. Okay, and so then now that we've decided to do all these things, the important question is, do they help? And in fact, they do. So this is the top line performance that we have. We have DQN in the top, Rainbow at the bottom. And it's worth mentioning that the architecture we're using is not the original DQN architecture where you have 3 convolutional layers and then 2 dense layers. We're using the ResNet architecture that was used by Impala. The reason for doing this is we've found time and time again that this architecture just works a lot better. We used it in BBF. We used it in our PVN paper at iClear last year. There's just been a number of papers that have demonstrated that this works better. So this is the architecture we're using here. That being said, in the paper, we do have results with the standard architecture, and we have the same type of behavior where MoEs helps in a similar way. Okay, so what we have here is the number of experts on the x-axis. And what does baseline mean with number of experts? What it means is we're just expanding, as I showed in that diagram before, we're expanding the penultimate layer by a factor equal to the number of experts. So this is the same plot that I showed at the beginning, arguing why scaling in DeepRL is hard. You can see that as we scale that dimensionality of the penultimate layer, the baseline sees a drop. If we go from like the standard dimension to 8x, you get a 20% drop in DQN and a 40% drop in Rainbow. With Soft MoE, which is our top performer, we can see that as we increase the number of experts, we actually get a 16% increase in performance in DQN and a 20% performance increase with Rainbow. So this is really exciting. This is quite nice. We don't see this sort of scaling trend with the top 1 MoE. As you can see in both cases, there's a drop in performance. In DQN, it's even like quite a lot worse than the baseline. So a lot of the analyses we end up doing are with Soft MoE, just because this is where we find most of the performance. And we'll discuss some reasons for why that might be in a bit.
Just a question on the previous plot. I think you said you will discuss some possible reasons why maybe the top 1 MoE is outperformed by the soft MoE, but I guess like in standard supervised learning, there's a lot of these issues with MoEs where like underutilization of experts.
Yep.
Do you think that could be one of the possible? I'm not sure if it was mentioned in the paper. I don't.
Yeah. So I'll discuss that a little bit.
Okay, cool.
Yes, that is something that could be a cause of that.
Okay, cool.
So one thing we also explored, because this plot here seems to suggest, as we add more parameters, you would hope that the network, the algorithm, your training process, whatever you want to call it, is using those extra parameters effectively. The blue lines here suggest that in the standard settings, they don't. As you add more parameters, it's actually hurting the performance. So it's kind of counterintuitive to what you would expect. But because we do see like a quote unquote scaling law with these soft MoEs, where as we add more parameters, we get better performance, we were interested in also looking at other situations where you want to be able to use, you would like the network to better use the parameters it has. And one of the aspects that we've been looking at over the past few years is the replay ratio. So the replay ratio is the ratio of number of gradient updates to environment steps. Right, so in standard Atari training for 200 million training, the replay ratio is 1/4. So that means that we take 4 environment steps before we run a gradient update on our parameters. So this is pretty low. You really want to be able to take as many gradient updates as you can so that you're learning as fast as possible, because we know that interacting with an environment can be expensive and slow. But it's been hard. It's really hard. As you can see here, as you increase the replay ratio, the performance starts collapsing. And we still see this downward trend with soft MoEs, but it's not as pronounced, and we're still maintaining an advantage. So there's, we haven't quite solved this problem with MoEs, but it seems to help a lot. We do have other work, like the BBF paper, for instance, where we do show how you can scale up the replay ratio and still maintain better performance. So, these are all just new techniques that we're uncovering that perhaps we should continue combining them like we did in BBF to get better and better agents.
Just to confirm, like on these two comparison, do you fix the number of environment steps or the number of gradient updates?
The number of environment steps is fixed. So this is for 200 million steps, and you just perform more gradient updates.
Okay.
Okay. So I mentioned all the design choices we made to run these experiments and get these positive results. And so we wanted to investigate a little bit like what the impact of these design choices are. So the first is the number of experts. So as we can see, for soft MoE, we seem to do better and better with more experts. There's perhaps a bit of a plateauing happening here. But in the baseline and the top one MoE, we don't see this phenomenon where you can add more and more experts. So this is something that seems to be really specific to soft MoE and the way the training dynamics happen there. So it's something we're still looking on, and then I have some results later that to discuss this a bit more, particularly with respect to top one MoE. The dimensionality of experts is also something that we were curious about. As I mentioned, we're just taking the same dimensionality of the original dense layer and just multiplying it by the number of experts. And see, we saw that we can, if you just scale it up, it doesn't work. But these experts, in the results I've shown so far, have the same dimensionality as the original dense layer. So in a hard gating setting, this makes a little more sense because, since you're having this sparse activation, it becomes a bit more comparable with the original network. But, in soft MoE, where we're doing basically activating all the experts, you want to have a bit more, the comparison is more akin to the scaled up version we have here. But we wanted to explore, well, what happens if we do the same thing, but now we just scale down the dimensionality of the experts? And in particular, what if we scale down for soft MoE, the dimensionality of the experts, we scale it down by a factor equal to the number of experts? And so that would mean that using this setup here, because we have these scaled down experts, now we're once again kind of more comparable to the original parameter size of the baseline. And so this is what we see here. This blue dashed line is the baseline performance, and green line is what we did, what I already showed in the last plots, where we're just keep the same dimensionality and just scale up by adding more experts. And then the pink bar is showing what happens if we divide the dimensionality of each expert by the number of experts. So we try to maintain parity in some sense with the original baseline architecture. And the takeaway from here is that there isn't a huge drop in performance. You can see these CIs overlap quite a lot. So the dimensionality doesn't seem to be hugely important. It's really, this suggesting is this kind of structured sparsity that comes from the use of mixture of experts really is yielding a benefit to the training of these agents. And so this makes also, if we look at this plot over here, if we look at number of experts equal to 1, right? This is essentially, you're just adding the dispatcher and the combiner matrix in the case of soft MoEs, right? You're not adding anything else. It's just one expert. So you're adding these extra parameters. We can see that in the case of DQN, it hurts performance, but it actually improves performance in Rainbow. So just adding this router seems to help. So one thing we did is, well, what is the impact of that learned router? So we replace that learned fee with just a random fee. So basically that matrix fee just gets initialized every time we do a forward pass through it. And you can see it still, learns, but it drops performance dramatically. So really the impact of this learned router is quite important. This is with one expert, right? So we're replicating what we have here. The learned router does seem to have a benefit in addition to the sparsity that we see induced by the combination of experts. And then tokenization. I mentioned 3 different tokenization schemes that we were exploring. We mostly focused on per conv, but we also looked at per feature, which is basically just a transpose of per conv, and this per sample, where you're sending the whole input, the whole state space, the whole state, sorry, to the experts. And we can see per sample doesn't work very well in either soft MOE or top 1 MOE. This confirms that the solid green line here confirms that per conv works quite well with soft MOE. What was interesting to see is that in the top 1 MOE, per feature seems to be quite a lot better than per conv, and it even is comparable to per feature with soft MOE. And it's starting to get close to soft MOE performance. So because we saw such promising results with soft MOE early on, we focused a bit more on that. But this result, to me, suggests that there's still lots of room to explore here. Like we haven't solved this. This is just sort of pointing in the direction that this idea of mixture of experts has a lot of merit, but there's lots of room for exploration here. And this is one of the areas I think where there could be more to uncover. This is coming to Caleb's question of the number of active experts. In top 1 MOE, there is this problem that people have observed in supervised learning, where you have what's sometimes referred to as expert starvation. So what ends up happening is that one or a few experts end up getting all of the tokens, and some other experts get starved, and they're basically useless, and they don't get used anymore. So what we ended up doing is there's been a few different load balancing losses that can be used. I won't go into the details of that here, but essentially these load balancing losses, what they're trying to ensure is that tokens are kind of distributed uniformly across experts, and also that experts are being selected sort of roughly uniformly. And this is the pink line here. So we can see in DQN, it doesn't really help at all. It actually hurts performance. And in Rainbow, it doesn't hurt performance, but it also doesn't really seem to improve at all. Maybe it learns a little bit faster, but not really. Like in the end, they end up being roughly about the same. So we have been doing quite a number of analyses on this. There does tend to be expert bias in the sense that some experts end up being picked more. And so you can add these losses, and you can roughly think of these losses as essentially trying to get uniform entropy, where you want the likelihood of the different experts is roughly about the same. But here numerics matter quite a lot. So if you have, let's say you have 4 experts, one expert has likelihood, and this is just very high level hand wavy, one expert has probability 0.26, and the other 3 have, I don't know, 0.23. That is almost perfect entropy, right? Like, or perfectly uniform distribution. But the 0.26 will always win, at least in the way, because we're doing this hard gating, where we're doing a hard selection. Of course, if you do sampling or something like that, perhaps it can help mitigate some of that. But in general, you have these type of more annoying kind of numerical issues that sometimes come up. Okay, so we did some analyses to try to better understand what's happening. And so what we're doing here is we looked at 3 games, and we were looking at the effective rank of our representations. You can check the paper for details. This is coming from prior work where they develop mechanisms for doing this. We're looking at the norms of the features that are produced by our MOEs, as well as the fraction of dormant neurons. So this is from a paper we published last year at ICML, where dormant neurons are essentially neurons that have become inactive. And what we showed in that paper is that once neurons go dormant in an RL setting, they stay dormant throughout training. And this is related to the plasticity of these networks that I mentioned at the beginning, is part of the reasons why we have difficulty in doing things like scaling up networks and things like that. So the main takeaway from this is that these mixtures of experts end up with higher effective ranks than the baselines, which is good because that is sort of akin to you better using the parameters of our networks. The norms of the representations are lower, which also tends to be make the optimization process a bit stabler and easier. So this is good and might be a part of the reason why we're seeing strong performance. And also we see a dramatic drop in dormant neurons, in particular when using soft MoE. So this is basically, it's not quite zero, but you can see just it's orders of magnitude smaller than both baseline and top one MoE. One important caveat to keep in mind is that these metrics seem to be, kind of consistent where we have, this ordering for the ranking where top one MoE interestingly has higher effective rank. Soft MoE has lower dormant neurons, but these aren't predictive of final performance. So we specifically pick these games because there are games, in Asterix, they both end up at roughly around the same performance. In Pong, they're the same. And Space Invaders, we do see a better performance with soft MoE, but it's actually kind of comparable to baseline. So these metrics on their own aren't enough to predict when these soft MoEs will really give you the better performance. But the trend that they indicate is there. So they're part of the explanation for why MoEs are helping. And it's still yet another avenue for investigation to figure out, have a better idea for why these things work. Okay, so one thing
question on the previous slide. Were like the optimization hyperparameters used across these methods similar?
Yeah.
Okay. So it couldn't be a side effect. Okay, cool.
Yeah.
Thanks.
So one thing we did in this paper is we explored quite a few things. And one thing I wanted to do is not just, future work sections and papers, they're always interesting and nice, but you can kind of put whatever there, right? You can just say, oh yeah, this is interesting future work. And, writing is cheap in a sense. But I actually wanted to start exploring things a little bit. And so with fantastic collaborators, we were able to do that. And so we explored the use of MoEs in a few different settings. And again, these are just sort of initial investigations into this. There's likely a lot more that you can do here, but what we show is that there's a lot of promise here. So in offline RL, we looked at two agents, CQL and CQL plus C51 that are, kind of standard, pretty well-performing agents in offline RL. And we can see, once again, soft MoE tends to improve performance quite a lot. And this shape that you see here, where you see an initial boost and then things start degrading, this is pretty common in these offline RL settings, where the more you train, the worse performance gets. Seems like the MoE architectures are stabler and better performing, so that's something encouraging. We also looked at low data regime agents. BBF that I mentioned before, that was evaluated on the 100K benchmark, which is a different benchmark for Atari, than standard 200 million environment frames. This one's 100K agent steps, which is equivalent to 400K environment frames. An interesting thing is the MoEs, we didn't see a performance gain in the 100K setting. Like there wasn't a degradation, but there wasn't a gain either. And in general, a lot of methods that shine in larger data regimes have difficulty kind of shining in low data regimes. On the flip side of that, some methods that work really well in low data regimes, like network resets, for instance, might not work as well in the larger data regimes. And this is something we observed in our dormant neuron paper, where we introduced this idea of resetting dormant neurons, which is, I think of it as a finer grained network reset, where instead of resetting the whole network, that can be pretty harsh, you just reset the neurons that are dormant. And that works a lot better than network resets in the high data regime, but doesn't work as well in the low data regime. So we found a similar thing with MoEs, but what we did find is if we let these low data regime agents like Dr. Q Epsilon and DER Dr. Q-epsilon, you can think of it as kind of the low data regime equivalent or analog of DQN, and DER stands for data efficient rainbow. So it's based on rainbow. And we can see that Soft MoE again just kind of outperforms all the others and has seems to have stabler performance in the sense that it doesn't seem to be plateauing, like the baseline seems to be reaching a plateau at some point. Another thing we explored, and I'm a little bit out of time, I don't have some extra slides from a different paper that's a follow-up to this, but we also explored different architectures for MOEs. So regular is what we use, where we plug the MOE into the penultimate layer of our network, but we also explored two different ones. So all is essentially using the plugging in an MOE at every single layer. So this is just for the dense layers. I don't believe we were doing it for the last two dense layers. Actually, no, I think we did do it for the conv layers. We had to do some shape shifting there, but I don't know if Timon ran these experiments, so he can correct me if I'm wrong. But we did plug the MOEs in all of the layers. And then big is essentially taking, rather than saying an expert is going to be a layer, an expert really can be anything you want, right? So you can say the full network is an expert. And now you can add put the dispatcher and the combiner at the beginning and at the end of the network. So you're essentially multiplying your whole network, and you're using these mixture of experts techniques. In this paper by Johan, Puigcerver and others, the Soft MoE paper, they demonstrated that normalization can help. So we decided to also explore that here. What we found is that in general, our setup, the regular setup, without normalization seems to work best, in particular with Rainbow. Normalization tends to hurt. And this kind of makes sense because the normalization that they introduced was really for very, very large mixtures of experts or large networks in general. So when we are using this big architecture where our expert is a full network, normalization might actually help there. And this is, in fact, what we see with DQN, where it actually even outperforms the soft MOEs. So I have I'm going to go through this very, very briefly. This is a follow-up work that it's not on archive yet, but should hopefully be up fairly soon. Some of the same authors, so Timon and Johan are co-first authors here. And so we wanted to explore this idea of MOEs a bit further in different training settings. So as I mentioned, non-stationarity in RL is something that is quite problematic. And so we wanted to sort of amplify this a bit and look at RL in amplified non-stationarity settings. In particular, we're looking at multitask and continual RL. So what is multitask? Multitask is as you're training, you're kind of getting a mixture of different environments. So this was run on Minotaur, which is a mini version of Atari. The nice thing about Minotaur is that you can, Timon's lab in Oxford, they developed these really neat vectorized environments so you can run them super, super quickly, hyper optimized with JAX. And so you can run, during training, like a mixture of these environments and train all of them concurrently with a single network and try to do well on all of them. And continual RL is quite a bit more difficult, where the training is split up into sections. So first you'll train, let's say, Asterix, and then you're going to switch over to Breakout, and then you're going to switch over to Space Invaders. Then you come back to Asterix, then Breakout again, and then Space Invaders again. This is all with the same network. So this is a lot harder because, when you come back to Asterix over here, you had to do a bunch of you were in a totally different setting. So your network is likely going to be forgetting things. And so it becomes quite a challenging task. And so we wanted to explore with this, amplified non-stationarity with different architectures. So this is our standard baseline. This is what we used in our previous paper, which is what I've been discussing for most of the talk. But we also added, this is called the final layer, where we add the MOEs instead of the penultimate in the final layer. All is what I already mentioned, where we add an MOE at each layer, and this is big. So I'll just go through this very briefly. I won't have time to go through this too much. We used first a hard-coded router, which is essentially an oracle that knows what game it's training on. So with the big architecture, this is essentially training separate networks, right? So you can see why in the continual URL setting, which is at the bottom here, when you come back to Space Invaders, you're essentially starting off from where you left off because you're effectively training different networks. But we were interested in exploring which of these different architectures would work best with a hard-coded router, and no surprise, Big ends up coming up on top. So then we wanted to explore, well, what if you start trying to learn these routers? And we still have hard-coded as a baseline here. And here what we find is something interesting, that Soft MoE, of course, you still have this performance drop when you come back to a game in the continual URL setting. But there's still there is some gain that is obtained from the continual URL setting that we don't see without using Soft MoE. So if you look at, for instance, Asterisk, it ends up at around 0.5 here. When it starts over here, this is not quite at 0, and it ends up at a higher point. So there is some transfer of knowledge from the previous learning. And obviously, this was a very initial exploration into this, but again, it shows quite a lot of promise for future work. And I think I'm going to stop there. Yeah, this is just kind of a takeaway and some ideas for why these things might be helping. The structured sparsity that induces. This is aligned with a lot of the work I've been doing recently. We put another paper exploring the use of pruning in DeepRL, and you can check it out. It's called in deep reinforcement learning, a prune network is a good network, related to some of this. And again, there's lots of open design questions, lots of avenues to explore. And I think it's an exciting space to be in particular, because it might be able to provide some insights also to the ever-growing large language model community. Thanks very much, and happy to take some questions.
Cool.